In this next unit, we're going to be talking about systems of equations. We're actually going to be talking about different ways that we can go about solving systems of equations that you haven't already seen in algebra. But before we get there, today our focus will be on how we have learned in the past to solve systems of equations, and we'll go over different methods that we've done this before. So take a look at the first example. We have 2x minus y equals 5 and negative x plus y equals negative 3. Now, in this example, we are going to solve the system graphically. That means I'm going to graph both of these equations and find where they intersect. So I'm going to take that first equation, 2x minus y equals 5, and I'm going to solve for y. So I'll subtract the 2x from both sides, and then that leaves me with negative y, and now I'll divide everything by negative 1. So I have y equals 2x minus 5. I'm going to represent this line with a red line on the graph, just to differentiate it between the other graph. All right, negative x plus y equals negative 3. I'll do the same thing, solve for y. So I'm going to add x to the other side. So we have y equals x minus 3. And I'm going to use this purple line to differentiate between the other graph. So y equals 2x minus 5. That means I'm going to start at negative 5 with my y-intercept. I'm going to go up 2 and over 1 and continue that. So that's going to be the line for the first equation. And for the second one, y equals x minus 3, I have a y-intercept at negative 3. And we have a slope of 1. So up 1 and then over 1. And we continue that. And there is my line. Now, in order to actually solve this, we don't just want to graph the two lines, we want to find their intersection point. In this case, it looks like the two lines intersect at this point here at 2, negative 1. So that is my answer. X equals 2 and y equals negative 1. Let's do another example where we solve this graphically. Y equals 2/3 x plus 2. 2x minus 3y equals 3. It looks like the first one is already in good shape. It's already in y equals mx plus b form. In the second one, we have 2x minus 3y equals 3. We'll get the y by itself. So subtract the 2x over to the right. Divide everything by negative 3. So we have y equals 2/3 x minus 1. Now, if I were to graph these, let's start with 2/3 x plus 2. I start with a y-intercept at 2. And I'm going to go up 2 and over to the right 3. Continue that, and that gives me this line here. Let's graph the second line. We start at negative 1 for our y-intercept, and then we're going to go up 2 and over 3. Now in this case, you'll notice that these two lines, they have the same slope, which means they are parallel to each other. So in terms of parallel lines, well, when do they intersect? Well, parallel lines never intersect. They don't intersect, that means that this has no solution. Let's do the next one. 3x plus y equals 1. 2y equals 2 minus 6x. Let's take the first one there. And we get y by itself. So we subtract 3x from both sides. So now we have y equals negative 3x plus 1. The second equation there, it looks like we can divide everything by 2 to get the y by itself. So I have y equals 1 minus 3x. Now if I wanted it to be in y equals mx plus b form, I would need to switch the 3x and the 1. So now I have negative 3x plus 1. Now if you'll notice, we actually have the exact same equation. They were just written in different forms. So when we go about graphing this, we have a y-intercept at 1 and a slope of negative 3, so down 3 over 1, and so on. And for the second equation, we have the exact same thing. And so when you're thinking about, well, what is the solution here? Well, if you have the same line, that means that when you graph them, one is right on top of the other. So where does it intersect? Well, if it's the same line and one is right on top of the other, it intersects everywhere along that line. So this actually has an infinite number of solutions. Now, this doesn't mean that x and y can be anything. It just means that there are an infinite number of solutions that you can find that will satisfy both of these equations. So essentially, any point that's on this line will satisfy this system of equations. So just to recap, we had linear systems of equations that we graphed, and we found that we can have exactly one solution. In terms of terminology, we call this consistent and independent. If we have an infinite number of solutions, that means this is consistent but dependent. Or we can have no solution, which is what we call inconsistent. And just as a review, if you'd like to have a picture for yourself, if you have two lines, they clearly intersect at one point, that system has one solution. If you have two lines and they're just really the same line, one on top of each other, then they have infinitely many solutions. And if you have two lines that are parallel to each other and they never intersect, then you will have no solution. Now let's take a look at how we have solved systems of equations in the past without graphing, just in terms of algebraically. So say we have here 2x minus y equals 7 and 7x plus y equals 11. So one method that you may remember using is the method of substitution. In substitution, you want to pick one of the equations, solve for one of the variables, and then substitute that variable in the second equation. So for example here, I'm going to take the first equation, 2x minus y equals 7, and I'm going to go ahead and solve for y. So y equals 2x minus 7. Now I'm going to take that and plug that into the second equation, the 7x plus y equals 11. And instead of writing y in there, I'm going to write 2x minus 7 in there. So this will be 7x plus 2x minus 7 equals 11. So that's the substitution part. Once you've done that, now everything is in terms of x in this equation and we can solve for x. So we have 9x minus 7 equals 11. So 9x equals 18, which means x equals 2. Now we're not done yet. We need to find both x and y in the system of equations. We found x is equal to 2. So what we can do now is we can plug that back into y equals 2x minus 7. And we have 2 times 2 minus 7, which is 4 minus 7, which is negative 3. So we've solved this system and we found x is equal to 2 and y is equal to negative 3. Let's look at example 3. Here we have 4x plus y equals 5 and 3x minus 2y equals 12. This time, instead of using substitution, I'm going to go through the process of elimination. So elimination, as the name suggests, involves adding the two equations together such that two of the terms, one from each equation, will be eliminated. Now, what you need to do is you need to first make sure everything is lined up in terms of the like terms. So we have 4x plus y equals 5, 3x minus 2y equals 12. So in this case, everything's already lined up. Now, we need to determine which variable we want to eliminate. We can eliminate the x term or the y term, but I would say that probably eliminating the y term will be easier because if I want to eliminate the y's, all I have to do is multiply the first equation by positive 2. If I wanted to eliminate the x terms, I would have to multiply the top equation by negative 3 and the bottom equation by 4. So there would be more work involved. So I'll take the first equation there. I'm going to go ahead and multiply that entire equation by 2. So now I have 8x plus 2y equals 10. And then I'm going to line that up with my second equation. And I'm going to add the two equations together. So the 2y and the minus 2y will now cancel. That leaves me with 11x on the left and 22 on the right. Now I can solve for x. Divide both sides by 11, and I get x equals 2. Again, we're not quite done yet. We still need to solve for y. Now it's up to you if you want to plug in x into the first equation or the second equation. Either way, you should get the same answer for y. I'm going to go ahead and put this in the first equation. So 4 times 2 plus y equals 5. So I have 8 plus y equals 5. And solving for y, we get y is equal to negative 3. So we have x equals 2 and y equals negative 3. We're going to do one last example. This one is not going to be 2 equations, 2 variables, but 3 equations and 3 variables. Now with 3 equations and 3 variables, you want to go about this by first picking 2 equations, eliminating a variable, and picking another 2 equations and eliminating the same variable. And then whatever you get as a result there, you'll be able to put together and eliminate one more time. Let's go through this process here. So let's say I take the first equation and the second equation. And let's say I want to eliminate y, because we already have a minus y and a plus y here. So I'll go ahead and add these together. I'll end up with 2x plus 4z equals negative 4. Now I can't solve anything just yet, but I have eliminated the y variable. So now I'm going to pick the second and third equations and put those together. And now when we add those two together, again, the plus y and the minus y will cancel. And that leaves me with 3x plus 5z equals negative 3. Now from there, what I can do is I can take those two results that I just found. Notice how they both have just x and z because in both cases we eliminated y. And now I have 2 equations and 2 variables. So let's go ahead and put those two together. Now I'm going to have to multiply the top equation by negative 3 and the bottom equation by 2 in order to get a negative 6x and a positive 6x. Once you've done that, we can start eliminating, and that leaves us with negative 2z equals 6, so z is equal to negative 3. Now we found z, now we need to go back and solve for x and for y. Now how do we solve for x? Well, we just found z, and here we had these equations just in terms of x and z, so pick one of those 2 equations to plug into. So we have 2x plus 4 times negative 3 equals negative 4. And that's 2x minus 12 equals negative 4, so we have 2x equals 8 and x equals 4. Now I have x and I have z. I still need to solve for y. Now I have to go back to one of the original equations that had things in terms of x, y, and z and go ahead and plug in. So let's say we take the first equation there. So we have 4 minus y plus negative 3 equals negative 1. And now I can solve for y. So I have 1 minus y equals negative 1. Negative y is equal to negative 2. And so y is equal to 2. So we actually solved for all 3 variables here. X is equal to 4, y is equal to 2, and z is equal to negative 3. Just as an overview of what we did in this problem where we had 3 equations and 3 variables, we started off by choosing 2 equations, picking a variable to eliminate, choosing a separate 2 equations, a different combination of 2 equations, eliminating the same variable as we did in the first pair, and then taking the results of those, which now are just in terms of 2 variables, and doing elimination on those, solving that, plugging back in to solve for the second variable, and then once you have 2 variables, plugging back in to one of the original equations to find the third variable.